So let's go to the next concept, compounds. So we'll discuss how to write the formulas and how to name compounds, and we'll also talk about the masses of these compounds. So let's start with the chemical formula. So what is a chemical formula? So a chemical formula generally consists of two things. One, it requires an elemental symbol and a numerical subscript. So the chemical formula generally indicates the type and the number of each atom that is present inside that particular molecule or the compound, and it's also represented in the smallest unit of a substance possible. Now, so let's start with naming binary ionic compounds. So the name itself says that for all ionic compounds, so the name and formula lists here are always to be cation first and the anion second. So what is the cation and the anion? So cation is the positive charge and anion is the negative charge. So the compound that has the positive charge gets named first. The compound that has the anion or the negative charge gets named second. So in a binary ionic compound, so both cation and anion are monoatomic, meaning that there is only one of each. So the name of the cation is the same as the name of the metal. Many metals in general end with em, so this is a common feature that you find it here. And the anion ends up with a suffix "ide". For example, calcium and bromine will end up forming, calcium will stay the same, bromine becomes bromide. So we basically take the name of the anion and in place of "ine" we end up making it "ide". So this is one of the common features that we end up with. Now, so what are the, let's see common cations and common anions and their names. H plus hydrogen, Li plus lithium, Na plus sodium, K plus potassium, Cs plus cesium, Ag plus silver. And plus 2 charges, you get Mg2 plus magnesium, Ca2 plus calcium, Sr2 plus strontium, Ba2 plus barium, Zn2 plus zinc, and Cd2 plus cadmium. And finally you have Al3 plus, that becomes aluminum. Let's look at the anionic charges. H minus is hydrogen, so we write hydride. F minus is fluorine, we write fluoride. Cl minus is chlorine, we write chloride. Br minus is bromine, we write bromide. I minus is iodine, iodide. O2 minus is oxygen, oxide. S2 minus is sulfur, we write sulfide. N3 minus is nitrogen, nitride. So this is how we write the charges based on the type of compound that is given. So where do you find the monoatomic atoms? Most common in the periodic table, you find it in 1A and 2A group elements, and the plus 3 elements are generally found in 3A, and most common elements, the anionic elements, are generally found in 5A, 6A and 7A. And some elements come under the classes in transition elements, some come under 4A group elements as well. So these are common places where you will find, but most main group elements are generally they have one monoatomic ion. Most transition elements have at least 2 monoatomic ions. So let's start naming these compounds. So what is the ionic compound that you get from each of the following elements? So here they are asking with magnesium and nitrogen. So magnesium here is a positively charged element, nitrogen is a negatively charged element, so you get magnesium nitride. In the same way, iodine and cadmium becomes, cadmium is the positively charged element, cation, iodine is the anion, so you get cadmium iodide. Strontium and fluorine, so fluorine is the negatively charged element, so strontium fluoride. Cesium and sulfur, so sulfur is the negatively charged element, which ends up forming cesium sulfide. So this is the idea behind how to name based on the "ide" suffix. So let's try converting this into empirical formulas. How do you write the formulas for these compounds? So I'll do the first one, and you can do the rest of them. So let me focus on magnesium nitride. So always remember to know the charges on what the compound represents. So if you remember, magnesium represents Mg2 plus and nitride represents N3 minus. So when you write the chemical formula, always write the positive first, so the positive comes first and the negative later. But there are charges on the top, so what you will have to do is cross the charges. So whatever is on the top will go to the other element's bottom, So here also the top will go to the other element's bottom. So what will happen here? The 3 on the nitrogen will come to magnesium, and the 2 on the magnesium will come to the nitrogen. So this is the element magnesium nitride. So let me take up another example. Let's say cadmium iodide. Cadmium is a common element with Cd2 plus, and iodide is I minus. So again the same thing again, same rule again. Always write the positive first and the negative after that, and cross the charges. So never write plus and minus, only write the numbers. Notice that there is 1 here, so Cd1 I2. So because 1 you do not mention it, so you can write it as CdI2. This is cadmium iodide. So in the same way, now try strontium fluoride and cesium sulfide. So strontium is Sr2 plus, fluoride is F minus, cesium is cesium plus 1, and sulfide is S3 minus. So try these compounds and see if you get the answer. Sorry, S is 2 minus. So now pause the video here and try to see if you can solve this problem. So all the atoms, all the compounds that we discussed now had metals where they can only form one ion, but some metals can form more than one ion. So for example, chromium. So chromium forms two ions, Cr2 plus and Cr3 plus. In the same way, iron forms Fe2 plus and Fe3 plus. You can also take copper. Copper is an element that forms Cu plus and Cu2 plus. So there are multiple versions of these elements that can take up these. So this is a table that shows you some of these elements and how to name them. So what we do when you have multiple elements that can form the chart, so what we do here in naming them is we write the element's name, and in parentheses in Roman numerals we represent the charge that the element can form. So this is chromium 2, and here this is chromium 3. In the same way, this is iron 2 and this is iron 3. This is copper 1 and this is copper 2. So these are what we call systematic names. There are also general names. For example, Cr2 plus is generally called chromous and Cr3 plus is generally called chromic. In the same way, Fe2 plus is called ferrous and Fe3 plus is called ferric. In the same way, Cu plus is called cuprous, and Cu plus is called cuprous and Cu2 plus is called cupric. So these are some common names that are given to the names that are originally based on the systematic names. So this is a table that summarizes all of them. So most of the common ones are chromium, cobalt, copper, iron, lead, mercury and tin. So these are the common ones that we end up with. So always remember, when you have an atom that can form more than one ion, then those ones are generally have to be mentioned based on the charge. So the charge is written in the parenthesis after the name. So we write the charge in the parenthesis after them without the symbol plus or minus. So let's try understanding a problem. So let's try to do some problems. So let's solve the first one. So here they have given us give the systematic name for each of the formula, or the formula for each name for the following compound. So they have asked us the first one, which is tin 2 fluoride. So let's look at tin here. So tin 2 is Sn2 plus. So we can write tin 2 fluoride. So there are tin 2 and fluoride. Right. So there are two parts in this formula. Now we can write tin 2 is Sn2 plus, fluoride is F minus. I told you, right? So exchange the charges. So you get Sn F2. This is the formula for tin 2 fluoride. Next you have CRI3. So when you're given the formula, how to name it, this is a tricky thing. So again, when you do this, you have to do the exact opposite. So remember that when you split it now, we have to take the charge. So chromium is separate, iodine is separate. Whatever the iodine number was, take that as the charge on chromium, and iodine gets the charge on chromium, so which was 1. So chromium is a commonly positive element, iodine is generally a negative element, so we can write. So iodine is minus. So iodine minus. Now we have Cr3 plus and I minus. So Cr3 plus is chromium, but chromium 3. Notice that Cr is a multi-atomic element, so which means that it can form more than one monoatomic ion. So now chromium, and I minus becomes iodide. So chromium iodide. So this is the structure. Now try the same for ferric oxide and cobalt sulfide. So for your easiness, cobalt sulfide. So when you take cobalt sulfide, cobalt is an ion that is 2 plus, and yes, here is 2 minus. So this is, now try to name the structure. So let's continue the naming part, and let's talk about polyatomic ions. So polyatomic ions are the ones where you see the internal structure having a covalent bond, but the overall structure having a charge. So NH4 is one of them, so which is ammonium, we call that ammonium. H3O plus, we call it hydronium. And these are common anions that you will generally see. So just go through the thing, and I'll explain it as we do an example. So one of the common ones that you'll end up seeing is oxygens attached to a carbon, attached to a particular element, having different names. So for example, when you take ClO4, generally if you take ClO3, so we start with ClO, this is called hypochlorite. So the name itself says, so hypo representing that less than usual. ClO2 is chlorite, ClO3 is chlorate, and ClO4 minus is perchlorate. If the root word changes, for example, if it is manganese, it becomes permanganate, hypomanganate, manganite, manganate. So these are examples of where you can see per and hypo. So, and the other names are for hydratic materials. For example, like when you have binary covalent compounds, you end up with more than one. So the numbers, if you have too many of one of them, so then these are the suffixes that we end up using, so to represent the number of those individual hydrates. So let's take a simple example. So let's take these three examples. Alright, so let's take this example here. So let's start with the first one, which is FeClO4 taken twice. So Fe here. So now if you want to split it, remember the splitting part. So this will go on the ferrous, and ClO4 will come on the other side. So Fe in majorly a positive charged material, ClO4 will become minus. So we have Fe4, Fe2 plus, and ClO4 minus. Fe2 plus represents iron 2. ClO4 minus is perchlorate. So if you want to refer to this, you can go back to the table and refer the name of that. So this is iron 2 perchlorate. Next, how do you write sodium sulfite? So sodium is Na plus. Sulfite is SO2 2 minus. So notice the structural names. So sulfite and sulfate. SO3 2 minus is sulfite. SO4 2 minus is sulfate. Now use that in case here. So SO3 2 minus. So this will go here, plus will go here. So this becomes Na2 SO3. So this is an example of sodium sulfite. Next here, BOH taken twice. So what is OH? So let us look back at OH again. So how would you write OH? OH is hydroxide. So you have Ba, OH taken twice. So take the first part of the problem first. So this is BaOH taken twice. So if you split it, you get Ba2 plus and OH minus. So Ba2 plus is barium, OH minus is hydroxide, right? So and you have extra 8 H2O. So H2O is generally written as hydrate. So there are 8 of them. So it becomes oxyhydrate, right? So it becomes octahydrate. So barium hydroxide octahydrate is the name for this compound. So this is how you can name the compound. So try this exercise here. So they're asking you to recognize incorrect names and formulas. So if they're asking you whether the formula is wrong or the name is wrong. So try it on your own and see if you can recognize if there is any problem with that. Next, let's talk about naming acids. How would you name acids? There are two types of acids. One is the binary acid and the other is oxo acids. So binary acids are acids that contain certain gaseous compounds dissolved in water. So for example, if you take HCl is an example of a binary acid where you're having a gas that's dissolved in water. So this is an example here. So when you write this, how would you write this? So we write the name hydro as the anion. So hydro prefix hydro plus the anionic metal root and then the suffix ic. Right. So here it is hydro. The suffix, the anion is chloro, so it becomes chlor, and then ic acid. So whenever we have binary acids that involve no oxygen, so there is no oxygen, we call them hydro acids. So we start with hydro. So whenever you see an acid in the front with hydro on it, it means that this is an acid that does not have. So this is an acid that does not have oxygen. So these are binary acids. Next is oxo acid. So oxo acids are similar to oxoanions, but the prefix is different. So in place of 8, we write ic. In place of ide, we write as. And we use prefixes hypo and per. So make sure that we name the structure. For example, if you take BrO4 minus, this is an example of a structure where you have, this is bromide. So this is hypobromide. So when you write the name of the acid, so we call it HBrO4. So we call it hypobromous acid. So whenever you have ite, it becomes as, it becomes ic. And one way of knowing which is hypo, which is per and everything, so one way of doing that is to look at, so for example, let's say HOCl. HOCl is hypochlorous acid. HOClO is chlorous acid. HOClO2 is chloric acid, and HOClO3 is perchloric acid. So HOCl is generally written as HOCl directly, but HOClO is generally written as HClO2. This is written as HClO3 and HClO4. So if it's just one hydrogen, that's hypo. Two hydrogens, so it is chlorous, us, and so if it is, the number of oxygens represents the compound. So if it is only one oxygen, then it is hypo and ic. If it is two hydrogens, then it is just us, OUS. If it is three oxygens, we have ic, and if it is four oxygens, you get per plus root plus ic acid. So this is how we name oxo acids, right? So try finding the acids based on the structures that they have given. So let me do the first one. So first one is Br minus. When you take it is bromide. So the acid becomes, so when you add H to it, it becomes hydrobromic acid. IO3 minus, so notice that there are 3 hydrogens, which means it's a ic acid, so it is going to be iodic acid. So cyanide is hydrocyanic acid. This is a sulfate, remember that it's a sulfate, so it's sulfuric acid. This is nitrite, it becomes nitrous acid. So this is how we can determine the names of acids. Next, let's talk about binary covalent compounds. So a binary covalent compound is typically formed when you have a combination of 2 nonmetals. So some of these compounds are very common and they have trivial names like water. So for a binary covalent compound, so the element with the lower group number in the periodic table is first in the name and formula. So its name remains unchanged. So the element that is second is named using the root ide. It's always common one. So you generally see ide a lot. So numerical prefixes indicate the number of atoms of each element that represent. So for example, if you take carbon disulfide, so carbon is C, disulfide is twice, so sulfur 2. PCl5 can be named as phosphorus, pentachloride. So they're asking you to give the name of the compound whose molecule consists of 2 nitrogens and 4 oxygens. So they're asking you for N2O4. So this is dinitrogen tetroxide. So whichever is in the first in the periodic table will get preference over the one that is later in the periodic table. So here try this problem and see if you can solve them. So the solution is down, but try to see it if you can solve it on your own. So pause the video here and try to see if you can solve it. Next, how to name straight chain alkanes. Alkanes are generally come from hydrocarbons. Hydrocarbons are compounds that contain carbon and hydrogen. So alkanes are the simplest form of hydrocarbons. So alkanes generally end with the name ane. So they are named after the number of carbons. If there is 1 carbon, the prefix is meth. If there are 2 carbons, eth. And in the 3 carbons, prop. 4 carbons, but. 5 carbons, pent. 6 carbons, hex. 7 is hept. 8 is oct. 9 is non. And 10 is dec. So, and they always end with -ane. So, for example, for 1 carbon alkane is methane, 2 carbon alkane is ethane. In the same way, 8 carbon alkane will be octane. So, this is how we can determine for straight chain alkanes. Next, let's come to the last concept, which is how to calculate the molecular masses from chemical formulas. So, the molecular mass is the sum of individual atomic masses. For example, when calculating the mass for H2O, we calculate the mass for 2 hydrogens that are present. So twice the atomic mass of hydrogen plus once the atomic mass of oxygen. So this is how we can find the value for molecular masses. So for ionic compounds, we refer to the formula mass since the ionic compounds do not consist of molecules. So we do not say molecular mass, but we say formula mass for ionic compounds. But both of them, they refer the exact same thing. So for example, if you take tetraphosphorus trisulfide, so tetraphosphorus trisulfide is P4S3. So it is 4 times the atomic mass of phosphor and 3 times the atomic mass of sulfur. So you can get these values from the periodic table, and when you add up, you end up getting the final value, and you can try it on your own. So here they are asking you for a particular problem. So try to solve this problem and see if you can complete the problem. So pause the video here and try to solve this problem. Next, let's come to representation. How do you represent molecules generally is there are 2 ways, one by formulas, the other by models. These 3 are what we call the formula representation of molecules, and these 2 are the structural representation or the model representation of molecules. So the most common representations as models is the ball and stick model and the space filling model. So ball and stick model is useful when you want to represent bonds, and space filling model is if you want to represent the actual space occupied and the shape of the molecule. So you will see a lot more as we go along in the chapter, but these are the two common ones that you are going to end up seeing. So the representation in general depends on these colors. So this is the most common colors that you will generally see. So if you want to just screenshot this part of the video and keep it as a reference so that you remember which color is what. So this is an example of representation of iron and sulfide. So this brings up the concept of last topic, mixtures. What is a mixture? Mixtures are compounds that are physically intermingled but not chemically combined. So homogeneous, there are two types of mixtures, heterogeneous and homogeneous mixtures. Heterogeneous mixtures has one or more visible boundaries. One way of looking at heterogeneous mixtures is when you have two different phases of compounds that are combining. For example, if you combine a solid and a liquid or a liquid and a gas, these are generally called heterogeneous mixtures. And these are ones that you can physically separate. So you can physically see the separation. So heterogeneous mixtures are where you can see physically the separation. A homogeneous mixture generally has no visible boundaries because the components are mixed as individual atoms or ions. So an example of this would be milk. An example of heterogeneous mixture would be sand water. For example, let's say put sand in water. So you can actually see the sand separately from water. But when you see milk, you cannot see the lactase molecules, the lactose components separately from water. So this is an example of a homogeneous mixture. So heterogeneous mixtures are called colloids. Homogeneous mixtures are generally called solutions. Right? So solutions, when you put them in water, we call them aqueous solutions. So that's the difference. So what are the ways of separation? So these are common basic separation techniques. So the first one is filtration. So filtration is where you separate the components of a mixture based upon the difference in the particle size. So generally it involves separating a precipitate from a solution. So an example of this would be, straining the water out of rice would be an example of filtration. The second one is crystallization. Crystallization is separation based on differences in solubility of components in a mixture. An example of this would be ice and water. So think about the differences in their separation. So for example, when you put ice in water, you notice a subtle difference between, you actually see the ice piece separate from the water. The reason it's because it's a crystal and its solubility is different. Next is distillation. Distillation depends on the temperature, and so we use temperature separation and the volatility to separate the mixtures. The next one is extraction. Extraction is based on the solubility again by in different solvents. For example, if you have a non-polar material, it might dissolve in a certain solvent, but a polar material might dissolve in a certain solvent. So these are examples where you separate them based on the solubility. The last one is chromatography. Chromatography is also based on solubility in a solvent versus a stationary phase. So when you have a stationary phase of a substance and when you shine light on it and it changes its phase, that is when you end up taking the changes. So with that we end chapter 2.